First of all, what I will talk with you in this lecture is what are the characteristics of calibration. We will go through everything about that. And let's start by calibration tolerance. Every calibration should be performed by a specified tolerance. The terms tolerance and accuracy are often used incorrectly. In ISA, there is the definition of these terms are different. For accuracy, the ratio of the error to the full scale output, or the ratio of the error to the output, expressed in percent span or percent reading for the instrument. And the tolerance will be different because it is a principal deviation from a specified value, may be expressed in measurement units, percent of span or percent of reading. Let's start with an example. You have a pressure transmitter to calibrate. I gave you this pressure transmitter, I gave you the range for the transmitter, and it is from 0 to 300 psi. The accuracy I gave it to you is 0.2, more or less 0.2 psi. And what I need right now I need this accuracy to be in the same unit of the other measurements. As you know previously, any pressure transmitter will have two types of measurement, in psi in the pressure and in milliampere, and that will goes to the PLC or the control unit. So how I will calculate this accuracy in milliampere? If we will say that the 300 psi will be equal to 16 milliampere, then we will do it as followed. We will divide 0.2 psi, and this is our accuracy, on 300 psi and multiply it by the current value of the maximum psi, and it will calculate for us the accuracy that we have in milliampere. So right now we have two accuracies, or one accuracy with two different units in psi and milliampere, and this what I should have. I always should have the accuracy, the tolerance in milliampere and psi in all the units that I will measure in it. So I have the accuracy from the manufacturer, but I don't have it in my measurement unit. So because of that, I need to convert this from psi to the measurement unit that I will use. So right now I calculated it is 0.1067 milliampere. I will round it to 0.10 milliampere. And why I didn't write 0.11? If I were approximately will try to find approximately for that, mathematically it will be 0.11, and that's it, milliampere. But I rounded down to 0.10 milliampere. That's because if I will write 0.11 milliampere, I will exceed the accuracy that I calculated. So what I try to tell you is I am in need to have the best accuracy. So writing the accuracy down is better than write it up mathematically, because physically I need it to be as accurate as I can. There is something else we need to discover. For example, let's say I have an accuracy for this instrument and maybe it is 0.25% of full scale. This is the manufacturer accuracy. The calibration tolerance should not be assigned based on the manufacturer specifications. Calibration tolerance should be determined from combination of factors. And these factors including the requirement of the process and the capability of available test equipment and consistency with similar instruments at your facility, and at least the manufacturer's specified tolerance. So I need to combine this all accuracy to find the tolerance that I will calibrate in it. And let's take an example. I have right now a process required from me more or less than 5 degrees Celsius. This process said I accept the readings more or 5 degrees. This is the tolerance that I am using in the process. Okay? So the process instruments acceptance at more or less 5 degrees. And they gave me the process equipment capable of reading 0.25 degrees. And the manufacturer Fluke in this example stated it is 0.25 degrees. So what the tolerance I will use in the calibration? I will use the tolerance of 1 degree. Why? I didn't just using this accuracy or this tolerance randomly. I must have a tolerance between the device specification, the capabilities of the device or the manufacturer specification, and between the process requirements. So my process requirement is 5 degrees Celsius and the manufacturer for the instrument said it is capable of 0.25 degrees, and the calibration process will be tolerance at more or less than 1 degree Celsius. And that's not just because it is between that, because I am using an accuracy ratio of 4:1 to do this. So what is accuracy ratio? This term was used in the past to describe the relationship between the accuracy of the test standard and the accuracy of the instrument under test. The term is still used in these days by these who do not know how to calculate uncertainty. And actually it is a good rule to ensure an accuracy ratio of 4:1 when performing a calibration. And what this 4:1 means? This means accuracy. When I say accuracy ratio of 4:1, this means that the instrument or the standard I use in the calibration should be 4 times more accurate than the instrument being checked. So if I will check the calibration tolerance and the process requirements, I will pass the accuracy ratio. It will be 4 times more accurate than the process requirement. It is mentioned here 0.25 degrees. This is the capability of the device, And let's see, I found it to be 0.5, not 0.25, but I found it 0.5 degree out of tolerance for the device requirement. Since we took into consideration an accuracy ratio of 4:1 and assigned a calibration tolerance of more or less than 1 degree Celsius to the process instrument, it is less likely that our calibration performance using that standard is compromised. So for 0.5 in my calibration process between the 5 degree, the process requirement, and the calibration tolerance is passed. Not out of the tolerance, but it is out of tolerance for the equipment. So the out of tolerance standard still needs to be investigated by reverse traceability of all calibration performed using the test standard. However, our assurance is high that the process instrument is within the tolerance. If we had assigned a calibration tolerance of more or less than 0.25 to the process instrument, or used test equipment with a calibration tolerance as the same of the calibration as same as 1 degree more or less, we would not have the assurance that our process instrument is within the calibration tolerance. This leads us to something called traceability. If I will find our process is not working or our standard is not in the tolerance, I need to do traceability. So what traceability means? Traceability means that all the calibrations should be performed traceable to a nationally or internationally recognized standard. And for example, in the United States, the National Institute of Standards and Technology, NIST, formerly National Bureau of Standards, NBS, maintains the nationally recognized standards. So, the traceability is defined by ANSI and CSL, and this number shown on the screen as the probability of a result of a measurement whereby it can be related to appropriate standard, generally national or international standards, through an unbroken chain of comparisons. And note, this does not mean a calibration lab needs to have the standard calibrated with a primary standard. No. It means that the calibrations performed, and notice that the calibrations, not only the calibration I did for my standard, no, the calibrations performed are traceable to an IST through all the standards used to calibrate the standard, no matter how many levels exceed between the lab and the NIST. And the traceability is accomplished by ensuring the test standards we use are routinely calibrated by a higher level reference standards. Typically, the standards we use from the lab are sent out periodically to standards lab, which has more accurate test equipment. So we have right now something we can manage from it, the traceability, called traceability pyramid, and this will include all standards starting from bottom. In the bottom, I will find my process instrument. I need to send my process instrument to a calibration lab or calibration shop and maintaining an accuracy ratio 4:1 to go from lower working level to a higher calibration standard. So first of all, I will trace the calibration process from the process instrument to the workshop or the lab that did the calibration. Then I would trace the calibration standard using in that lab with a secondary standard using a higher level with at least accuracy ratio 4:1. After that, I will trace this secondary standard to a primary standard, higher primary standard that have also accuracy ratio between the secondary and the primary standard 4:1, and goes by traceable directly to national measurements standards with also ratio 4:1. So right now, when I trace my equipment from lower level to higher calibration, and higher, then goes to NIST, for example. This called my calibration process is traceable for NIST. And right now, after knowing all that about traceability, what we need to know is more fundamental. If I don't know something called uncertainty, I cannot do calibration. Okay, I know the accuracy, I know the tolerance, I know how to trace the calibration process, but there's something fundamental to understand and called uncertainty. And the uncertainty is a parameter associated with the result of measurement that characterizes the dispersion of the values that could responsibly be attributed to the measurand. And what I called measurand is different than the measurements. I measure things using a device, the device called measurand. I record the readings from the device, that's the measurements. So there is difference between measurand and between measurements. So right now, uncertainty analysis is required for calibration labs accredited with ISO 17025 requirements, and it is performed to evaluate and identify factors associated with the calibration equipment and process instrument that affect the calibration accuracy. And calibration technicians should be aware of basic uncertainty analysis factors such as environmental effects and how to combine multiple calibration equipments accuracies to arrive at a single calibration equipment accuracy. And how I will calculate that? Combining multiple calibration equipment or process instrument accuracies is done by calculating the square root of the sum of the squares through these two formulas. So calibration, as you see right now, calibration equipment combined accuracy, it will be squared until all the squared for the cubic, the sum of the cubic of the squared calibrator error 1, calibrator 2 error, and the other calibrator's error that I will have, other environmental, all the errors in the time that I did the calibration, I will double it, I will square it and and do a sum for it, and then after that I will do a root square for it. Process instrument will be a little bit different. I will take the sensor error, the transmitter error, the indicator error, and do the same formula. And why this is different? Because in calibration I am using standard or more than one standard, and calculating the environmental effect and other effect, human effect, interruptions, all these errors I am calculating. But for the process instrument I need to have monitors in my site. I need to have transmitters, indicators, sensors. All these things have errors. I will calculate it. So right now we have reached to the end of our lecture. I hope it is in use to you in your future. In the next video we will explain the certificate, the calibration certificate, what it contains. After that we will do a reverse learning strategy. I will make you learn from the uncertainty, starting with the uncertainty and finishing with the calibration device, or the device under test information. So right now subscribe, keep watch for new videos. Goodbye.